run one using the air track. So before I go into all the physics stuff, we'll just try to keep the same thing that we did last time, where if the air is off on the track, that the rider is not on the track. So make sure you communicate with the group across from you. If you're going to turn the air off, make sure they're not in the middle of the run. Okay, so you just don't want the carts to drag along the track. Okay. Today, you notice the track is not at an incline. And actually, you're going to want to use the levers if they're here to make sure that it's not on the incline. The levers are here. If not, you can try to use that other method that we did before, where you put the cart in the middle, not attached to a string, and make sure that it doesn't move. But anyway, we'll work on that later. So today we're going to focus on Newton's second law, F equals ma, for a two-body system. And the two bodies are going to be the cart that's on the track, and then this mass that's connected to the pulley, and the system of pulleys that's going to be providing the main source for the motion. So the picture looks like this. I'll call this big M. Big M will be the mass for the rider on the track. This is the mass of the cart. And then it's attached to a string, which goes over a pulley, which just changes the direction of the string. And that's attached to a hanging mass. I'll call that little m. So for a frictionless surface here, which this air track is going to kind of be, we can do free body diagram for both these objects. So I'll do free body diagram for the cart. And I'm going to do a free body diagram for the mass, the hanging mass. And since this is the positive x direction and these guys are connected, I'm going to call this the positive x direction too. You're free to do that, Why am I doing that? Well, if this thing is accelerating, this thing is also accelerating with the same amount. If this has positive acceleration, this has positive acceleration because they're connected by a string. So if I have two coordinate systems, the coordinate systems have to be connected. So when you have systems connected by a pulley like this, sometimes this is what you want to do. Anyway, so what forces does this guy feel right here? There's a force due to gravity, so that's big mg. And then there's a normal force, which is going to get canceled out with this. This is the force on the big mass due to the track. And no friction, so the only other force is the tension pulling it this way. And then for this guy, it only has two forces on it. It's got little mg, its weight, and then up it's got tension. And it's the same tension. Why is it the same tension? I did a little derivation in our workshop class, and I'm not going to do it right now because it's kind of long, but you can show that for a light string that's not stretchy, the tension is the same throughout the whole string. Also, as long as this pulley is considered to be light, which for our experiment it will be. In a real world situation, the tension here is actually greater than the tension here, but it's such a small difference that it's not going to mess with our experiment too much. So we've got these two free body diagrams with these equal tensions. So over here, nothing going on in the y direction, so if we sum up our forces in the x direction, we get tension, that's all there is. And since that's the only force, the sum of the forces doesn't equal 0, so it must equal ma, so this equals big Ma. Over here, we sum up the forces in the x direction, and we get mg minus t. And that equals ma. Little ma. So we can see t is the same, and t is big Ma. So I'm going to put that over here. So I have little mg minus big Ma, because that's what tension is, okay, is equal to little ma. So let me solve for A. Let's see, what do I want to solve for? 1 second. Okay, there's a few things I can solve for. We're going to do two different experiments, so let me make sure I get this let's solve for this one. Let's solve for mg. So experiment 1. Solving this equation for mg, we get mg is equal to big M plus little m a. Okay. For the first experiment, what we're going to do is we're going to plot mg versus a. What is this going to look like? So what we're going to do for the first experiment is constant total mass. So if you look on Canvas, you'll see that you're going to do like 5 different runs. And with the first one, you start with some mass that you put on top of big M, like these little coin masses. They're here at the end. And so you'll put like a little coin here, and you'll have like a bunch of the coins like sitting here. Okay? So there's always going to be a different amount of mass on the big M than there is on the little m, like added to it. But for every run, you do one run and then another one, you're going to move one of these guys to here, or vice versa. I forget which way it is. It's written in Canvas. Okay? So the total mass of big M plus little m is always going to be the same, but you're going to have a different driving force. Okay? It's like this guy gets more massive, or this guy gets more massive, either way. Okay? So we can see that if we plot acceleration versus mg, where this is the hanging mass, however much is on the hanging mass, this should be a linear equation, or a linear function with a positive slope given by m plus m. And that's a constant. What do I mean? So like, if you go in Canvas, for example, and if you open up this week's experiment, if you look at the part that says lab report, for week 6, let's see, we're on Tuesday. So you go in and you look at lab report for week 6 for Newton's second law of motion. There's a table there. So I already showed you exactly what table to make. I kind of made it for you. So for the first run, okay, you're going to have 80 grams added to the cart and 20 grams added to the hanger. So that's a total of like 100, plus the mass of the cart and the mass of the hanger, okay? Then you take one of the 20s from the rider and you put it on the hanger. So now you've got 60 and 40, but it's still 100 plus the total mass. Then you do another 20, so you got 40 and 60, but it's still 100, right? So the total mass, which is the cart plus what you added to it, and the hanger plus what you added to it, is a constant positive value. That's going to be the slope of your data points for the 5 different runs. 1, 2, 3, 4, 5. And obviously you're going to fit, okay? So this, how do you get this information? Mg and big M and little m use a scale and you find out what it is. So the question is, how do you get A? Well, we're not going to use paper and spark tape today. We're not going to use a high voltage source. It's not connected up. Instead, we've got a cool computer system with a little laser in here and a wheel with spokes that spins and cuts off the laser at a certain frequency depending on how fast this thing is moving. So that data is automatically going to give you velocity as a function of time in this laptop, which I'll help you set up. Okay. So if you have velocity versus time graphs, what are you going to pull off of it to get your acceleration values? Exactly. So you'll have a different velocity versus time graph for every run. You'll zoom into it and find like a nice linear area and get the slope of that linear area. Pull that slope, that's your acceleration. That's your data, okay? So acceleration 1, acceleration 2, acceleration 3, acceleration 4, acceleration 5 for little m1g, little m2g, right? Okay? Where this is how much mass is on the hanger. Make sense? Et cetera, et cetera. G is 9.8 meters per second squared. Okay. That's the first experiment. Second experiment, experiment 2, you're going to plot, let's move this big M over here. So we got mg, so same equation is equal to big M plus little m A. Okay, and then let's solve this for A. So A is equal to little mg divided by m plus m. This is the second experiment. So for this one, bless you, is constant total mass. This one is going to be constant hanging mass. But you're going to change the rider mass each time, but the hanger stays the same the whole time. Constant hanging mass. That's little m times g. So this is a constant. So this is also a linear equation, okay, with a slope of little mg if you plot A versus 1 over big M plus little m. So A versus 1 over big M plus little m. Okay. That's going to change. That's going to be a variable because you're kind of always going to change your hanging mass, your little m. No, always going to change your big mass. Oops, sorry. Big mass. Big M. All right, well, Freudian slip, can't undo it. All right, so the slope here is little mg. I'll be thinking about that all day. Okay, and that's positive. Okay, so this is also going to be a positive slope, but different from this one. So what's the slope? This slope is equal to big M plus little m. This slope is equal to little mg, hanging mass times g. That's always the same. That's right. Little m times g. Little m times g. For this one, you're going to be constantly adding more mass to the rider, but you're going to keep the hanger the same. Okay? So the goal, and you're going to get the acceleration the same way. You get the acceleration from getting the data from the laptop. Okay. But what do I want to say? Is that, oh yeah, and so what I want you to do is then to see if the physics worked is to do like a nice percent difference where this is your actual, so the actual value is the slope, that's that m plus m, okay, like what you get from this linear fit, the slope. The theoretical is actually m plus m. So literally the sum of the two masses. So is m plus m actual measurement. And remember, that's not just the added masses, but the added masses plus the mass of the carts. So you're going to need to weigh your carts too. And so to get percent difference, you'll do actual minus theoretical divided by theoretical times 100%. For this one, your actual value is the slope that you get from the computer. In this case, it's little mg. I mean, you're not putting in little mg or anything, and this is theoretically what it should be. I should just put slope. It's the slope, but it's a different slope from this graph. And the theoretical is mg, little mg. So this is the mass that you weigh times 9.8 meters per second squared. Okay? And then you'll do the same thing. Actual minus theoretical divided by theoretical times 100%. And it's not going to be 0% because, you know, there's friction and all these things, but you should expect a pretty small number, like less than 10%. I think that's not unreasonable. But just check Canvas for what the lab reports or requirements are. I don't think there's really anything else I need to say unless there's questions. What I would do is first detach your hanger from the string, or the, what's it called? The riding cart from the string if it's attached, and go over to the beam balances and get a good mass measurement for it so you know what big M hanger, the cart's value is. The hanger might say what it is, but you can always, like it might say 50 grams or 15 or something, but you can always weigh it just to be sure. And then just go on Canvas and do the 5 runs where you have a certain amount of mass added to each one. Make sure that you communicate about turning on the vacuums. And if you need help setting up the laptop, the lab manual tells you how to do it. But if you get stuck, please try to do it with the lab manual first. But if you get stuck, just call me over and I'll help. I think in the lab manual it tells you to use the big one and the small one. Let's see. I think you could use the red. It shouldn't matter. You don't think it shouldn't matter. As long as you weigh it and you know what it is, the physics doesn't depend on each. So they should be okay. But stick with the same cost that I started. Okay.